Uh, Thanks everyone for joining. My name is Murat Kantarcioglu. I'm an associate professor of computer science at University of Texas at Dallas. I also have a visiting appointment at Harvard Data Privacy Lab, and also we have a spin-off from our lab called DataSecTech. So today I'm going to talk about our data security and data privacy research, especially how we would like to rethink some of data security aspects in the presence of new AI and ML developments. So let me go ahead and turn. So just to be consistent and everyone on the same, to be on the same page, I guess everybody is aware of the fact that the data is ever increasing. Now we have this big data revolution happening that is really impacting everything. And with the big data revolution, especially in the data storage, data management space, we see newer tools out there, newer storage and processing models like Apache or Apache Spark. And in addition to that, in the last 5-10 years, almost every organization is moving into cloud, and most of them now have some kind of hybrid options, like some of the data is on their premise, on-prem, some is in the cloud. And of course, all this data, people want to leverage this data to build new revenue models, to build newer services. And therefore, we need to do AI ML on it. And of course, now we need to really secure the data while doing it. And what we also observe is that in addition to security, the privacy becomes an important issue due to data compliance requirements. Of course, for those who aren't super familiar with big data, the four important characteristics is that we have huge volume. In other words, we get more and more data. And that's the reason we need new data management or data processing systems out there. And I think one important fact is that compared to maybe relational databases, you would have a variety of data. So you would have structured and unstructured data. So when I mean by unstructured, it would be like text or image. Semi-structured could be like JSON or XML. And of course, you have the relational database, which is already the workhorse of the corporate world. And then, of course, the velocity these data keep coming. I think for security purposes, important aspect is that it's incomplete in the sense there may be some noise in the data, such for IoT applications. And also it would have other incompleteness and data cleanness issues. And the important thing is that, at least from our vantage point, is that there is no one data system where all this data is residing. And many organizations we talked would have different data management systems where they manage these data that they require for AI or ML, ranging from NoSQL database systems to data warehouse systems in the cloud to MySQL type SQL databases. And when you're doing AI on all this data, you really need to consider this diversity in the data storage, data processing, and data, and so on. So now, what's the challenge, at least in our research, that we try to understand and address? We really need to protect this big data against cyber attacks, and this is really important issue because big data is critical for many organizations. That's like their crown jewel, where they will get lots of value. And we see that new cyber attacks are happening against this big data, and that those attacks could be devastating from privacy point of view to corporate risks and also liabilities. And while we are doing this AI, of course, we need to really think about regulations. In Europe, there is the EU GDPR. In California now, there's California privacy law coming to a. And our observation is that really there is no simple, effective way to protect all these data across all these databases, whether it's NoSQL, SQL, while doing AI and ML. And therefore, what we notice is that different organizations or different databases that have their own solution, and it's not really uniform. Of course, in addition to really worry about these, how to protect all this data in very different places, ranging from on-prem databases to cloud, of course, you need to worry about additional things such as the cloud by itself can be attacked, whether you can trust the cloud. So that's clearly, in other words, additional security issues with respect to this data landscape or data management landscape. Now, there are many databases sitting in the cloud. Of course, if you look at the entire pipeline, so there is this data management, and you want to build AI models itself, and then these models can be attacked. And I will give an example of what I mean by such attacks. So in other words, now, in addition to databases and the data that could be attacked, now you have an additional thing to protect, which is the AI and the ML model itself against attacks and so on. And the flip side of that coin is that these AI and ML models could have implications with respect to privacy and security. And I'll try to give an example of course, this requires many different solutions, and these challenges are not by itself easy to address. So I will talk about 3 different pieces where we try to address some of these challenges in the amount of time. And then if there are any questions, we can go more deeper. First, I would like to talk about one solution idea we developed for addressing the issue of the data sitting in the cloud, and we want to do machine learning data mining on the data, and how we could really leverage cloud without really trusting the cloud. And of course, this problem has been there for a while, and there are many solutions developed. One solution is really focused on encryption. And the main idea in the encryption is that you store the data encrypted in the cloud, and then you process this encrypted data and get the results, for example, encrypted results. And of course, there are many different protocols developed over the years, and either they don't trust anything but not very efficient, or they are very efficient but they're not very powerful. In our line of work, we looked into a different angle, and we tried to leverage secure hardware. What we call, here is an example called Intel SGX, which is Intel's extension to its chipset, where you allow a program to create an encrypted enclave, and all the memory contents of this enclave is encrypted in memory, and only encrypted inside the CPU. And you can run the program or your solution inside this enclave. And the security is guaranteed by the hardware. There were some attacks against this architecture, like the hardware attacks, but some of it need to be patched, and some already patched. And also, of course, another important thing is that this just encrypts the memory. And in a cloud setting, it's been shown that you have to design your programs to prevent further attacks due to the memory access patterns of your program. So the programs that are leveraging this hardware needs to be carefully designed, and it shouldn't disclose any additional information, because the hardware only gives you the guarantee with respect to encryption of the memory contents. And this is not far-fetched. Actually, today, you can deploy solutions on Microsoft Confidential Computing Cloud, where there is a support for this hardware. So today, you can deploy a solution like ours to the Microsoft environment. And now, what's our goal? What do we want to achieve using this hardware? Remember, this hardware allows us to do some processing inside this encrypted memory. But of course, we want to make sure that it doesn't leak information, because hardware has only limited support. So the goal is to really protect the secrecy and integrity of the big data and the ML models using this encryption and the hardware support. And what we have done is that there were some specific solutions that leverage this hardware before, but it needs to be really custom designed for the task. Let's say you want to build a certain machine learning model, you have a very specific solution just for that model. In our case, we developed a general language that allow you to build your own models. But remember, if you have a general language, then all these leakage issues come into play. So we want to make sure that our limited general language allows rich set of data analytics and still don't disclose this memory access patterns or this other side information that could be attacked. And of course, you want to make it general and efficient enough. So what I mean by this memory access patterns and what are the issues with that? So imagine that you have a secure hardware, all the data is encrypted, and you want to run this piece of code inside that secure hardware. And remember, what this hardware IntelliSGX, for example, allows you to is that it just encrypts the memory content. So a cloud provider or a malware sitting on the cloud won't be able to see the memory contents, but it would be able to see which memory locations your program is accessing, because that's not hidden for efficiency reasons by the hardware. So what's the problem with that? So for example, imagine you want to write a simple Python code, something like this, and you want to, could you please mute yourself if you are not going to ask a question? I hear some people. Okay, so if you are, let's say, want to ask, compute average income of individuals older than 50, and you have this simple Python code to do it. The important issue is that if the attacker knows, let's say, you want to run such program, then this if statement and the memory access patterns associated with this if statement, even if the memory contents are encrypted, will be observable, because you would be jumping to different memory locations while you are accessing this if statement. And this would give an attacker, allow attacker to observe like how many people who are really over than 50, for example. So this will leak some sensitive information, even if the entire program and the entire data is encrypted. So what's the solution? Our solution is to simply vectorize. If you have a vectorized versions of these things, so this var function simply returns a bit vector on a vector of inputs, and it will say 0 or 1 whether a person satisfies this constraint, whether it's bigger than or equal to 50. So it will return like a bit vector. So if the user is satisfying this constraint, it will return 1 for that location, otherwise it returns 0. And then we do a dot product of this vector and then just divide by the number of sum of this vector s, which is the how many of the individuals are older than 50. And what you could prove is that this second version does not leak any memory access patterns. So in other words, whatever the data distribution is, the second one will have exactly the same memory access, but this one does not. So therefore, we make it data oblivious. In other words, whatever the data distribution or memory pattern access will be similar. So of course, designing an entire system is challenging. I skip many details, but you have to really, when you're doing this hardware, you really need to divide things into trust and trust components. And in our case, we have this basic library we have that's trusted and execution engine and so on. And the optimizers and other things such as compiler are untrusted. So you write your code and it will be compiled to our framework and it will be executed on the encrypted data and you would get your machine learning model. So the compiler simply get this Python-like language and it will compile it into basic commands and make sure that everything is data oblivious and all the operations are vectorized. So this is a simple Python code to do linear regression. and it will map it into simple operations in our system so that you could execute it. And of course, in order to support data science, we implemented basic SQL and matrix operations that are oblivious and secure. So we had this secure library that you can build all AI ML and easily leverage all this hardware. One couple of things in the interest of time I'm skipping is that making this code not to leak sensitive information when running on encrypted data, you really need to analyze the code and make sure that the users don't disclose anything sensitive. And what we can check for is that for certain leakages, we can check in the code and we can warn the user. And the other thing is that for those who take a database class, you know, query optimization is an important part of a database. So we want to do similar optimizations here, but we want to do them securely. In other words, our optimization shouldn't depend on anything sensitive about the data. So we have this entire optimization framework that leverages this hardware and it's secure. So if you look at this, you can process a significant amount of encrypted data using our big matrix framework. Like you can do things like PageRank and linear regression in minutes or seconds, depending on the dataset size. But importantly is that if you compare this to another solution, for example, that just use pure crypto, you would see that even simple matrix multiplication, if you are just using pure crypto solution, obliviously will cost hours. In this case, it takes basically seconds using hardware. Of course, the downside is that, just to be fair for the crypto solutions, is that you have to trust the hardware in our case. So we are now trusting hardware, and we are now really making sure that data is encrypted and only decrypted inside the hardware. So this is another solution, as I mentioned, compared to pure crypto approaches that use like homomorphic encryption or circuit evaluation. Here, by using hardware, you would be getting significant performance improvement, build your models on this data, encrypted data, and make sure the data is kept encrypted and the models are encrypted. So this is one option to really secure in the cloud. Now, but still, this has some limitations, and still you are sending encrypted data to cloud. And in some scenarios, you may not even want to send the data to cloud, and you may want to send maybe less information, even if it's encrypted. So for those reasons, in our work, we looked into something called federated learning. This has been developed and deployed by many companies such as Google. And the main idea is that you don't want to even send the data encrypted to a central place. So if you could, then the previous solution would apply. But let's say you don't even want your data to be sent encrypted to cloud. And here the idea is that there is a central server. Let's say this is wants to do machine learning model on something let's say for image processing. And then the central server decides a machine learning model. It could be like a deep learning, like let's say some CNN model, and then sends the initial parameters to several nodes. This could be like different organizations, hospitals, companies. So the initial model is sent to the several different nodes or organizations, and each party trains the data, trains the model on their local data, and send these trained local models to the cloud, and the cloud aggregates it and send the aggregated thing back to those nodes or organizations. So now you don't even send the data, you just send model updates. And of course, the central server could aggregate it using a solution like ours, like trusted hardware, or crypto. Here, since you are sending entire data, you are just sending updates. Crypto solutions also somewhat applicable. So the question is, what can go wrong? It turns out that if you stop sending, if you do something like this, it turns out that the model itself can be attacked. So these are called backdoor attacks. So these are like targeted or misclassification attacks via data poisoning or model poisoning. What you want to make the machine learning model to learn a trigger pattern. So for example, you want your machine learning model to work correctly most of the time, but whenever a plus sign added to the picture, you want model to misclassify it. In other words, whenever normal picture of 1 given to the machine learning model, it would classify it as 1. But the minute plus sign is added, it would classify it as 7. So in a sense, you are kind of building a backdoor into this machine learning model so that anytime you want, you could make that machine learning model to malfunction or make mistake. Of course, this is a simple example, but you may imagine scenarios where, like you can put a sticker maybe on the stop sign, and then suddenly you can make a car to maybe crash targetedly. For example, you can target certain individuals, for example, to have car accidents, let's say. But it doesn't happen all other times. So those kind of backdoor attacks could be very serious. So in our work, we try to look into preventing it, especially in the context of federated learning. In the federated learning context, you don't send data, so you send models. And what the corrupt or attacked party could do is that it can send poison updates to the server to cause it to learn this backdoor. So this is especially very powerful attack against a basic federated learning approach called federated averaging. In the federated averaging, what you do is that you simply get updates from each party or each site. You weigh it based on the instances that site has, and then you normalize it, and you have a learning rate, and that would give you the next update for the model. So now the attacker who controls this delta TK could change it to push the model towards its goal where there is a backdoor learned by the model. So in order to prevent this, our main idea was to adjust the learning rate of aggregation per round and per dimension based on the updates of the sign. So in a sense, as I will explain a little bit more, each agent, based on its update, will be voting to go to one direction. Based on those votes, we decide which direction to go. So our procedure, in a sense, tries to go to the direction where most of the participants agree. Okay, and this is a very simple but effective solution because we don't change even the underlying averaging scheme, but we change the learning rate and the learning direction actually. So how this thing work? We have this hyperparameter called theta, and what we are doing is that we look at the sign of the update sent by each agent or each site at each time. And if it is higher than a certain threshold, or in other words, if there is an agreement in the direction, we do the regular learning rate for that direction. Otherwise, we went to the opposite of that direction. So the main assumption is that attacker will not be able to control more than a certain amount of parties. And by looking at not just looking at the direction, we can have a feeling of where to go or which side to go. The important thing is that this learning rate is done per dimension of the model, basically. So there is not a central thing. When we look into this, and when we look into this solution in the context of federated learning, where maybe 10% of the agents, nodes, or sites, which are used interchangeably, are corrupt. And we look into this in two different settings. One is called IID, where we assume that each site has somewhat similar data distribution. And we look at the setting also called non-ID, where the sites may have different distributions. And of course, in this setting, three things is important. What happens like to your classifier when there is no attack? What happens to your classifier under attack? And how successful is the attacker? Okay. So if you look at it from regular setting, if you are using like standard federated averaging, and if you do this attack couple of rounds, what you would notice is that validation accuracy, in other words, your accuracy on clean data sets, look like doing quite well. And when you test on the clean data, it looks also good. But what will happen is that after a couple of rounds, attacker's backdoor becomes highly successful. So therefore, the standard averaging is very vulnerable to these kind of attacks. But if you are using this adaptive learning rate approach we propose, at least for these type of attacks, the backdoor attacks that is evaluated, we can show that the attacker's attack is not very successful after even many rounds. And also we have proof that our scheme still converges. So we have nice convergence properties. For non-ID setting, and actually we have more follow-up scenarios where the data distributions are slightly different, then the things are slightly harder for both learning. And also attacker may have slightly better success because the differences in different sites may be leveraged in this setting. So therefore, non-ID setting is slightly harder. So just to show, compared to other defenses, if you look at our setting, when we have like federated averaging with a regular attack, backdoor is successful 100% of the time. So in other words, attacker may force model to learn this, let's say, plus sign as a backdoor almost 100% of the time, and it's successful almost. And at the time of we did this published in AAAI last year, some other options in practice wasn't very successful against these more advanced attacks. In our case, ours was very successful. But one important thing is that compared to regular thing, of course, we have a slight drop in the accuracy. So in other words, our solution makes the accuracy a little bit dropped. We also look at the non-ID. As I mentioned, in non-ID, our defense is slightly less successful, but still attack success is like only 3% or so. But now we have a slight more drop in the accuracy when there is no attack, where the regular case is 99% accuracy. Our model, when there is no attack, is now 97% accurate, this training scheme. So I try to now give a flavor of the fact that, remember, we try to build models securely using encrypted data, and even the sending data was not maybe acceptable for security reasons. We look into sending model updates, but now these model updates become potentially vulnerable, and now we developed a solution to this, and we show that this simple defense works well for at least the existing type of attacks we had at the time. And I skipped many other details about like distributed backdoor attacks and a few other settings. Now I would like to switched a little bit and in the last 10 minutes or so talk about the last piece I mentioned, which is the AI and ML models implications on data privacy. So even if you build a model on using encrypted data, even if you throw some federated learning, I didn't talk about differential privacy, but other privacy preserving measures. The question is, what does these models could leak about you, and what are the social implications? And over the years, probably you've seen news items such as, oh, your Facebook likes expose your personality. You know, if you like certain websites or certain things, you know, it will say something about your even claim of intelligence. Or your profile picture can reveal your satisfaction with life. You know, if you smile more often, apparently you are more satisfied. You can apparently look at Twitter followers and use machine learning to see whether some life event happened, because now you follow a different set of people. So all these things are machine learning models somehow built to impact potential privacy of the users and infer sensitive information. And there are, this is from a real research that claims that if you like curly fries, you are slightly more likely to have higher IQ. Apparently, if you are liking iPods, you are a little bit more dissatisfied with life. Computer scientists are apparently more likely to be shy and reserved, etc. So these kind of findings using AI and ML has maybe misused by themselves. For example, some might try to infer something sensitive about you, such as your sexual orientation or your political affiliation and other sensitive things. So now we try to use this attacking as a other side of the coin and protect maybe privacy. So in the previous work, I showed how we can build models so it's much harder to attack and insert maybe backdoors. Now we want to use attacks as a way to protect individual privacy. So what we developed is that, but of course, while we are doing these attacks, we want to be ethical. So that's the biggest difference, I would say, than attack. So we have some cost function. In other words, we want to change our Facebook profile or maybe take a new, better picture. I'll show you an example of it, or some other change you want to do in your information, so that once you change your profile, your CV, your tweets, etc., from X to X prime, you want some machine learning function to classify you in a desired category. So in other words, let's say I would like to change my CV so that an AI model wouldn't just throw my CV out. Or I would like to change my Facebook profile so I would look attractive to an AI model, so they would maybe promote by, let's say, posts. Apparently, there are some things out there that claim that attractiveness is a measure in promotion. I don't know if that's true or not. So you could have such a goal that you want to achieve with respect to this machine learning model. But of course, we want to constrain it in such a way that it's maybe ethical and it's maybe also legal in a sense. So you don't want to lie in your resume, for example. Of course, let's say if you say you have a Ph.D. without having it, maybe it increases your chances. But then, of course, it would be a lie and it would be illegal. So you want to modify the CV. Still, the AI and ML model would think that, oh, this is a great CV, let me pass it to the human. But still, you don't lie, for example, because it would be not ethical. So that's the constraints we are after. So I will give you one example. We have an entire framework where we applied this on, like credit card applications to other scenarios. Here I'm talking about why we start this work by looking at pro-sexual orientation in a country like US. This may not be an issue, it's possible. So let's say our picture somehow so that it will be classified whatever we want. Of course, for IRB and privacy reasons, we couldn't really do the sexual orientation goal. Instead, we looked into something simpler. By the way, we tried to replicate some of the studies out there. We believe that prediction of someone's sexual orientation by profile pictures is overly exaggerated. I think at least the capacity to do that. So in our case, what we tried to achieve was that, okay, let's put some maybe glasses on pictures so that AI model would change its prediction. As I mentioned for IRB, our IRB didn't allow us to do research on actual orientation. Instead, in order to show that this is quite feasible, we looked into the setting where we attack a gender predictor. So we get some publicly available data sets and we attack some machine learning model, and the model predicts a gender, and it does it 95% of the time. It can correctly say that this is a female or male. Of course, there are, I know it's not binary, so in this case, we just look at the binary case. So we put these generated glasses on it, on the pictures to see whether we can attack the model. And for these random close like 500 plus pictures, attack was successful 100% of the time. What we mean by attacks is successful. Let's say this image is classified as, let's say, male. Now, once you put this, it becomes female. Of course, our main goal was to make it something like glasses, for example. Of course, it's not super realistic per se, but you could do other constraint versions of this attack. As I mentioned, we tried some credit card applications, and it turns out changing some couple of things, you could find a very low-cost solution to now get your credit approved, for example. So to summarize, today I tried to talk about how we could protect data by using maybe encryption and secure hardware to build models. And then I tried to talk about how to protect models against attacks in a distributed setting like federated learning. And finally, I tried to discuss this flip side of securing machine learning against attacks versus attacking machine learning for privacy, and how, of course, they are somewhat connected. But of course, trying to emphasize that attacking ML for privacy, we want like ethical and legal options compared to general attacks. So that's, I would say, the biggest differentiator. Of course, this entire AI security ML intersection is much richer, and we even us have many more work. But I'm hoping that at least for the attendees, it would give some flavor of the challenges going on. So I would stop here and answer any questions available.